We're starting section 15.3, partial derivatives, and then first we discussed tangent lines on surfaces, basically some curves on surfaces, partial derivatives, and notations and higher order derivatives. So what was the story with the single variable functions? For a single variable function f of x, the derivative f prime of a at point a and f of a is the instantaneous rate of change of f of x at x equal to a. For example, over here, the instantaneous rate of change of f with respect to x is 5 here, whatever x value that is, and whatever y value that is, the instantaneous rate of change of f of x at that x value with respect to x is 0, and so on and so forth. And values can be positive and negative, and that rate of change tells you about the slope of the tangent line. Now, for a function of multivariable, for one variable function, there was only one direction, x direction, that you could see the rate of change. So what happens with a function of multivariable inputs? So here we had only one input, and in that direction, the instantaneous rate of change is that. So what happens in multivariable, even though we have infinitely many directions going to a point? Points, for example, won't be a and f of a, would be a, b, and f of a, b. So we have infinitely direction going to that point, so rate of change could be defined in any direction, but two directions are special to us. One is in direction parallel to x, one is in direction parallel to y. So this whole story of finding instantaneous rate of change in direction parallel to x or parallel to y actually starts there or is the concept partial derivatives. So let p equal to a and b be a point in the domain of function z equal to f of x and y. Fixing y equal to b results in a single variable function g of x equal to f of x and b. So if I put b for a constant b for y, I get f of x and b. And so this is going to be a function of x only because b is constant. Now the only variable, the only input is going to be x. So now I can define the derivative in terms that we defined for single variable. So this is the entire story. When you're fixing b, then that is y equal, when you're fixing y, that's y equal to b, that's a plane, y equal to b. And so intersecting with y equal to b, the surface that this is the graph of the function, the surface that is the graph of the function intersects with the plane in this blue curve. And the blue curve at point a, b, and f of a, b, remember it was x and a and f of a for a single variable. Now the input is two two variable inputs makes it a, b, and f of a, b. And so at this point, you're finding the one single variable derivative of the blue curve, not the entire surface, but just the blue curve. And so the slope of this tangent line to the blue curve at that point is called f sub x of a and b. So that's the formal definition of the partial derivative with respect to x at a and b. The other way that you read it, so you either for notation you read f sub x of a and b, but it's partial derivative with respect to x of f at a and b, partial derivative with respect to x of a and b. And so since g is a function of x, we can calculate the derivative g prime, and then g prime of a is the slope of the tangent line. But what is g prime of a? That's just basically derivative g prime of a is called partial derivative of f of x and y with respect to the variable x at the point a, at a point AB. Now, so we discussed partial derivative with respect to x. Let's do partial derivative with respect to y also, and learn the definition of derivative for partial derivatives. So briefly, first let's do a comparison with partial derivative with respect to x of f and partial derivative with respect to y of f. So comparing the two, when you're trying to find the partial derivative with respect to y, then you set x as constant. That means that intersecting it with x equal to a, and then you find the derivative of this blue curve that is the intersection of the plane x equal to a and the graph of the function. And so that derivative is going to be the slope of the tangent line to the curve right there. And so that's the difference. For partial derivative with respect to x, you set y equal to constant, and then you take the derivative. For partial derivative with respect to y, you set x equal to constant, and then you take the derivative. This also can be expressed into in a limit definition. And so how do we do this? That's a limit as h approaches 0 of f of a plus h and b minus f of a and b over h. This, do you see this? Only the first variable is changing. Second variable is constant. This is a partial derivative with respect to x. Other forms of writing notations for partial derivative is this round thing, round f of f with respect to x, and f sub x as we learned so far. I'm going to write this notation down because sometimes seeing it handwritten is easier for your mind. So you go around f and around z, and then you evaluate it at a and b, for example. Or you can put the a and b with a big line and on the bottom, basically. Or you can write around z with respect to partial of z. We read a partial of z with respect to x, and or you write it as f sub x of a and b. And so all of those are okay to use. And if you want to see the notation for partial for limit definition of the derivative in terms of partial of z with respect to y, this time it would be limit as h approaches 0 of f of a plus b plus h minus f of a and b over h, and this time only y changes. So we discussed what partial derivative really means geometrically and how it makes sense. Now, to compute the partial derivatives, let's say to compute the partial derivative f sub x of a and b, so partial respect to x of a and b, we apply the usual rules for differentiation, but we treat x as the variable and y as a constant. So you always remember y is the constant. It doesn't, and so that's important to do every time. To compute the partial derivatives f sub y of a and b, we apply the usual rules for differentiation, treating y as a variable and x as a constant. Partial differentiation is not an implicit differentiation. So let's do example 1. Let's try to take the derivative with methods that we discussed of the function f of xy equal to x times y minus y squared. So remember, let's first write down derivative. I have two of these, right? Derivative respect to x, and I can have derivative respect to y. This one also, other notation is that. This one, other notation is this. And so when I'm taking derivative respect to x, I have to set y equal to a constant. So if I write this, and let's ignore the y, and then I put the y in, let's imagine y is number 2, right? Just for the purpose of this. And so the derivative with respect to x is going to be 2. What is the derivative of 2y? It's just 2. But 2 is not there, right? It's just y. And what is the derivative? Let's write that down. So y. And then what is the derivative of what is y squared? It's just 2 to the power 2, right? And so that's 4. Derivative of 4 is 0. So this one is 0. So the entire thing is going to be y. Now let's do the same thing for derivative of respect to y. This time, write down we have to set x equal to a constant, right? And so this time, don't write down x, write down the y part, put a different color. It helps the first time that you're taking derivative a lot. So you take the derivative with respect to y this time. And so x is completely constant. And so when you're taking the derivative, x is a constant. Let's say x is number 3. 3y. What's the derivative of 3y? Is 3. But there wasn't any 3. It's just x, right? So x, right? And then minus y squared. Derivative of y squared is 2y. Again, x was constant. Constant times y. What happens with constant times a variable? Derivative of that is just that constant. And so what you got is y and x minus 2y. Now let's try to evaluate this at, let's say, 1 and 1. So f sub x of x and y is equal to y. F sub y of x and y is equal to x minus 2y. Now, f sub x of 1 and 1 is going to be, for you plug in 1 for y and 1 for x, but you don't have a x in here, so it would be 1. What about f sub y of 1 and 1? Plug in 1 for x, plug in 1 for y, and it would be negative 1. So the instantaneous rate of change of f when x varies at point 1 and 1 is 1, and the instantaneous rate of change of f when y varies at point 1 and 1 is -1. And these are telling you about the change in z with respect to x and change in z with respect to y. I click here question 15.3a. Let f of x and y be sine of 2x plus 12y. Find the partial derivative f sub y of -36 and 6. So stop the video and work it out and come back, please. So partial derivative with respect to y. That means that you're supposed to keep x here as constant. So when I'm taking the derivative, first of all, there's a derivative of outside and a derivative of inside, and with respect to y. So derivative of outside is cosine evaluated at inside, unchanged. Then you multiply that by derivative of inside. What is derivative of inside? 2x is just constant. Let's say x is 2. 2 times 2 is 4, so it's just constant. And so that one becomes, derivative of that one is 0. Derivative of 12y is 12. So this entire thing is 12 times cosine of 2x plus 12y. Now you're plugging in. So in here, you're evaluating at -36 and 6. That is for x, you plug in -36. So it's 12 cosine negative 2 times -36 plus 12 times 6. So it's 12. 2 times -36 is going to be -72. 6 times 12 is plus 72. Cosine of 0, it's equal to 12. And B is the answer. I click here question 15.3b. Which of the following partial derivatives, derivative calculations would require use of quotient rule? A, partial respect to x of y squared over y squared plus 1. B, partial respect to y of xy over y squared plus 1. C, partial respect to x of x times y over y squared plus 1. D, partial respect to x of x plus y over y plus 1. Pause the video and think about it and come back. So the first one is partial with respect to x, and y has to be constant, so the entire thing inside is constant, so it's not it. And part C is with respect to x, and x only appears in the numerator. Part D is again with respect to x, and x only appears in the numerator. Part B is with respect to y, and y appears on top and the bottom. So B is the answer.